So happy new year to you. So A, B, C, D option. You can choose the one you like, or you like more than one. Also, you can have one, or you can get one of yourself. So let's get started. First session on of year 2021. And topic today we are going to continue the topic of properties of solids, which we just started in the last session. That was a year back in 2020. So now let's going on and very quickly let's have a recap. The properties of solid. One common property and one very property we easily understand is, unlike liquids and gas, solids have different shape and size. But though it doesn't appear to so, but they do deform under external force. They undergo change in their dimensional change, and that's what this topic is. What the deformation of solid object is, and different types of deformation. And when we discuss behavior property of a object, so we rather see many things. How much an object will deform, it would depend on the size of the object. That is not property the material the object is composed of. So make it property of a material. To get rid of size effect, we use certain parameters which make it independent of size of the material. It becomes property of the material. So what we do in that case, there are two things here. Basically, we are discussing effect of force and deformation. So force also we divide by area on which it is acting. It becomes stress. So we get rid of the size parameter. Similar way, when we talk of deformation, we talk of relative deformation. What is relative deformation? Change in dimension divided by original dimension. And these two ratios lead to what you call elastic modulus, and there are three of them. So collectively, elastic moduli, that's what we are going to study, three of them. And all three are based on what kind of stress is applied and what type of deformation is taking place. So we differentiate different deformation in three distinct forms. So that's what we need to understand. One very quickly I had done earlier in last session. In this case, it's like a thin wire. The force applied and deformation both are measured in the same direction. And we assume this force also when we take area, which area we divide by? We divide by area of cross section. Area is the normal vector to the area is along the force vector or opposite. So thus area and force, we divide force by area, it becomes stress, and we measure strain, change in length divided by original length. This is Young's modulus. First one, stress by strain, longitudinal stress by longitudinal strain. Second case is you can think of if you have a cylinder which is fixed at the bottom. In this case, force is not applied. Force is applied perpendicular to the area vector. So here, and whenever force is have component along the surface, this is called a shear force. And force divided by this area here. Force lies in the area. Which area we divide by? We divide force by area in the plane of the force. And what kind of deformation takes place here? Here the deformation like this here, this is deformation. So if you apply force like this, it may get deformed like this. This is change in dimension and original dimension, they are mutually perpendicular. Like previous case, delta and L are in the same direction. Change in dimension and original dimension we divide by are mutually perpendicular, and this becomes like an angle. So since they are mutually perpendicular, this being very small, theta is equal to delta x by this L here. This is shear. And shear deformation, you can also visualize pushing a book here. And finally, so this is Young's modulus, longitudinal stress by longitudinal strain. This is shear modulus, shear stress by shear strain. With stress, you understand what the area divided by and how do you measure the strain here. And third is bulk modulus. In case of bulk modulus, it is not force. What is applied is pressure. Pressure is something we assume pressure. It acts from all directions, and pressure we take the perpendicular component. So in this case, the shape of object doesn't change, only its size changes. You notice here, this was the original boundary. If you apply pressure, it becomes compressed here. And this is something in this case, there's pressure is the stress here caused by area, and strain is volumetric. These are three things, and shear is something people find little difficult to understand. So you can also visualize shear something like this. If you have a piece of rubber, just imagine you have a piece of rubber. keep it glued to the bottom surface. Apply a force along the surface here, what will happen? And you can, when you push it, you can sense that rubber is pushing against your hand. When you're pushing it, there's always resisting force. All cases, when we apply an external force, you can feel as if the material is applying a force in the opposite sense here. So this also here, this also here, and the material is pushing back. So in this case also, if you try to push the rubber towards right, rubber will tend to push it towards left in this direction. And this is how it will get deformed. So this is what we, three things we need to understand, three kind of modulus. Longitudinal stress by longitudinal strain, shear stress by shear strain, volumetric stress, which is pressure by volumetric strain. And each of these three ratios, the dimensions are same. All ratios are, the unit is Newton per meter square. Strain is dimensionless. Only the nature varies. Stress strain ratio is property of the material. That's a unit. And this is the part what we have done in my last class, Young's modulus. And I'll just skip through this part we have done, Young's modulus. What we understand here, change in length when we apply a force, it's equal to FL by AY. For a change in length is proportional to force. And when we apply a force like this, material is applying a resisting force in the opposite sense. Very similar to spring. So when the rod gets elongated, which direction it has, uh, change in dimension is towards right, and force applied to the material is towards left. So this material or any material like wire, behavior is very similar to behavior of a spring. So we can compare this one to a spring. Any wire or a cylinder or any such shape, uniform product, we can compare it to spring. And in this case here, spring, we compare this equation. This term YA by L is equal to spring constant. That's what we have done. And energy stored also something similar to 1 by 2K into delta square. It becomes equal to 1 by 2F into deformation, Y 1 by 2F. The force also increased gradually from 0 to F. So average force acting is F by 2. Then we also did energy stored per unit volume. And energy stored per unit volume, we have done it earlier also. Which two chapters we have done energy stored per unit volume? We have done energy stored because of electric field. In that case, energy density was equal to 1 by 2 epsilon naught into E square. So any space wherever electric field is present, there's an energy stored. And we also did wherever there's magnetic field, there also there's a energy stored. There the energy stored was something like this. Okay, and this energy is stored per unit volume. So what is energy stored in a particular space? We multiply by the volume of that space. It becomes energy stored in that space. So similar way, so whenever an object is applied, it is acted upon a force, it has undergone deformation. There is a longitudinal strain. There is energy stored in the rod. And at each part of the rod, energy stored will depend on these two parameters. Energy stored will be 1 by 2, stress by strain. But any space, stress and strain are related. So I can write in one of the parameters. So strain also can be written in form of stress. Strain is equal to stress by y. So it becomes 1 by 2 into 1 by y into stress square. That's the energy stored per unit volume. So only two, three things here in Young's modulus, delta L, how does delta L connected to how is delta L varies with force, one part, and what is the energy stored here. And we can compare with the spring. And very simple, this is the only formula which you need to use here. Yes.
Sir, is this like a reversible process, like in case of a spring? Like,
Yes,
does it?
they're all elastic property. So basically all cases, why they're resisting, they're trying to come back. See, if we apply force to clay doesn't exert a resisting force. That doesn't have elastic property. So here, all cases we are whichever strain we are talking about, all cases, if we change the dimension of force, this deformation also will change. So which also means if I remove the force, the dimension also will come back to the original dimension. They're all reversible and elastic property. And this is what we had done last time. And I will not go through it. And this part you should remember, greater strength. Okay. And this also we had done. If I apply a force, only thing what we have to remember in this case, if any weight is suspended. So in this case, if wire mass is small, so when a weight is much larger than the mass of the wire, every part of the wire we can assume tension to be constant. That's what we had done last time. Now let's look at one more part here. A heavy rod of weight W, cross section A, length L is hanging from a fixed support. So this weight is suspended. Young's modulus is Y. Uh, neglect lateral contraction. Basically, what happens if you see a piece of rubber, you stretch the piece of rubber. In case of rubber, it undergoes significant deformation. If you notice, the cross section of rubber also will contract. So whenever one dimension increases, some other dimension may decrease, which will come to this part will come to the last, which is Poisson's ratio. So in this case, we neglect lateral contraction. Since we neglect lateral contraction, we assume the area to remain constant. Because if lateral contraction is to be taken into account, area of cross section may change. You don't have to take care of lateral contraction. So what is the elongation of rod? If heavy rod is suspended, even light rod also doesn't matter. So let's see what way it is different from previous case. What are the key points here? We understand change in length is equal to force, length of that element divided by area of that area of cross section, and this is material property. In this case, what we notice, force is varying with y. As the force is varying, I cannot directly use this formula. So what we need to do here, we need to consider rod to be composed of several small pieces. And this kind of integration we have done multiple times. We should be comfortable, and we just I'll quickly go through. So again, here also we imagine the rod to be several small pieces. We will take up a random piece here. What is a random piece? Random piece, if I take this y dimension at coordinate y, and length of this piece equal to dy. If I take random piece extending from y to y plus dy, tension in this part, what will be the tension acting on this part of the piece here? The tension acting in this piece, since the length is small, I can assume tension to be constant. Ty will be equal to weight of the part of the rod below this point. That's what the tension will act here. So if lambda is mass per unit length, the total mass of from 0 to y, the mass of entire this part here will be lambda into y. This becomes mass of and into g. This becomes the weight below this point here. Weight. Okay, so this becomes the force or tension which is acting. So this is the tension acting at a point which is at a height of y from the bottom piece, and length of the piece is dy here. Only thing I have taken up this one, you notice there are two small quantities. dl also small, dy is small. But we have, yes, it's one of rare cases we deal with such two cases, but this is also simple. So this will be the change in length of this small piece of length dy. Of course, this quantity will be extremely small. But yes, the small things do add up to a significant quantity. So this is change in a small piece, extension of the entire rod. Very simple. We add up all the extension. It's a scalar quantity. So we add up all the extension, we integrate from here, and we get this expression on integration. And this expression we can also write as w by 2 into L divided by Ay. Now we try to understand here what has happened here, why it is W by 2. And this part also is easy to understand. Why it is easy to understand from here is something what, see, if you look at what is the force acting on different parts of the pieces. The piece extend from y is equal to 0 to y is equal to L, and weight also or tension which is acting also is increasing linearly from 0 to, so this is how the tension will vary. If I draw the tension here, the tension is varying in a linear fashion. This is how the tension is varying at different pieces, starting from 0, and here the tension will become W. So what we understand here, if the tension varies in a linear fashion, I can take average tension, which happens in any integration. If integration involves a quantity which is varying in a linear way with the variable, I can take average of the number. This is W by 10 into A by. So that is another way you can understand. When force varies linearly, then extension corresponds to average force. Okay, and just understand here, I'll do one more thing here. Suppose the length is L. I don't want to know what is the extension of the whole rod. I want to find out what is the extension of the top half of the rod. So if I have top half of the rod, only thing what will happen, limits of integration will change. If I'm looking at top half, starting from y is equal to 0, so which part I'm concerned about? I'm concerned about y is equal to L by 2, y is equal to L. That will be the limits of integration. And when I integrate, I get an expression. I have rewritten in a certain different form. Let's try and understand what this form means. Is this form also matching with this or not? So when I'm taking what is the extension of this part here? Starting from here, starting from point where tension is W by 2 to a point where tension is W. Here also I notice tension there also is varying in a linear fashion. So what is the average tension here? So if I look at tension, what is average tension here? Average tension here will be equal to 1 by 2 of W plus W by 2. Okay, and that becomes equal to TW by 4. So this is the average force which is acting on top of the rod, and length is L by 2 and AY. So this is also applicable here, and this becomes very useful in some of the questions. Very thing only when it has to, this point we have to keep in mind when it varies in a linear fashion. So I will take a couple of examples where we can use this particular result what we obtain here, and if you apply it becomes makes it a little easier to solve certain questions. So let's look at some more questions here. So there's a uniform rod mass M, and this rod and cross section area is A. So force waste in the area here, area is perpendicular to the rod here. Area is constant and is placed on a smooth surface is being pulled by constant force F acting at the front end. And this is very common. So we apply force, and every time we assume the force is uniformly distributed over cross section. What will happen? Of course, the rod will get accelerated. If mass is m, rod will have an acceleration A is equal to F by m. Very simple application of Newton's law of motion. But the question is, if it has a Young's modulus, since tension is acting in different part of the rod, it will also undergo deformation. Its length also will change. And since the force is tensile in nature, it will have elongation. How do I find elongation in this case? So again, here what we find, some of you may think if I apply force F here, if other side also force F was applied, in that case tension would have been uniform, rod would not have moved. But here the force is applied only on one side. Tension will not be same in uniform. Tension here, it is F here, and the last part the tension will be 0 here. The tension will vary from 0 to F. So those who have doubt, just brush up your laws of motion again, a small piece, and I will come to some example which will help you understand why the tension will vary. So tension the rod varies uniformly from F to 0. Here the tension is F and less than tension is 0. So what is the average tension? Again, if I look at tension also, if I mark the tension here, this piece to this piece, the tension varying like this. And it is varying in a linear fashion, and laws of motion, very easily I can prove the tension is varying in a linear fashion. So if this dimension is X here, this is how tension is varying. And here also, since the tension is varying linearly, the deformation will correspond to average force. Average tension is F by 2. Hence, what would be the extension? F by 2, length of object, and divide by AY. That is the extension of the rod here. It's also a fairly simple case. Okay. An extension of the entire rod, and okay. And sorry, I think this part is repeated here. This part is from the previous sheet. Now come to next question. This question becomes a little different from previous one. What we notice here, so here also the front end, somebody is pulling with the force of TF through some mechanism, and it is being pushed also from the rear end. You notice the front end, the force is pulling in nature. It is like tension, and this force is trying to compress the rear part here. So one side force is tensile in nature, other side force is compressive in nature. So heavy, and it's a uniform cross section area placed on uniform surface, and two ends are they're acting in the same direction. What is the extension of the rod here? I can do it two ways. One way I can think of, okay, force in the front end is 3F tension and force in the rear end is compression. So is it in this case also, is it possible to mark if I take this point as x is equal to 0 and this point if I take x is equal to L, can I mark how would force vary as a function of x here? Notice here, see this is something, if this is x is equal to 0 and this is x is equal to L. If I plot tension as a function of x here it is 3t. So if I take tension as positive, I'll mark the force is equal to 3t here. And sorry, 3f here. And here it will be compressive nature. So if I have compressive, see tension is positive, compression is negative, and this would be F. And in between, the force will vary in a linear fashion, and that we can easily find out using laws of motion. So how the force is varying. Now, how do I find extension? And which point will the tension become 0? What does this point indicate here? This will be equal to L by 4, and this will be equal to 3L by 4. And so from the rear end at a point, this part of the rod, which is at 1/4 of the length from the rear end, this part will not experience any tension or a compression. That's how the force will vary. And rear L by 4 length, compression will vary from 0 to F. So I can find change in length in this part. It is varying from 0 to F. So what is average force here? F by 2. So hence delta L1, change in length in the rear 1/4 of the length, average force F by 2, length is L by 4. I get this expression. And similarly, I can front end also, I can calculate this part also. This length 3L by 4, average force is 3F by 2. 3F by 2, length is 3L by 4 divided by AY. This extension. What is the net change in length? If I take net of this, this is compression and this extension. So net delta L, which would be sum of change in length of the rear part and the front part, will become equal to, okay, it comes to pretty neat expression. It comes equal to FL by 8AY. Okay. So I'll just come to this part. Okay, just let me finish and then we'll see here. What is the other way you could have done rather than taking this approximation or using shortcut method? I could have also solved using laws of motion. See, how do we solve using laws of motion? How I can laws of motion, how we can solve it? So let me find what the force would be as a function of x. So what we have done here, from rear end, I have taken a piece of rod of length x. And I can calculate what would be the force acting in this cross section, which is at a distance x from here. Is it possible to calculate force acting or tension in the rod? So I have taken the force the way I have drawn the force as a tension. Can I find Fx as a function of x? Let's see how do we find out and what basis we'll find out. The force will act. We have done this. I am applying laws of motion. I have taken what part of the system? I have taken the rear x length of the rod as my system. And this part of the system also will have same acceleration as the whole rod. So based on applying laws of motion, I can find Fx as a function of x. And once I have Fx as a function of x, I can, through integration also, I can change the length. So tension is a function of x from the rear end. This is the net force. Net force will be equal to mass of this piece. Mass will be m by L, it's mass per unit length into x. This net force. So I'm just writing F net is equal to m into acceleration. Acceleration is 4F by m, whole system. So this gives me value of Fx. And once I have Fx value, Fx, this value of Fx which comes to, and you notice what is Fx here when x is equal to 0. When x is equal to 0, Fx becomes equal to minus F, compressive. And when x is equal to L here, what is the value here? It becomes 3F. And all other in between points also, we have an expression. And now through integration, also I can calculate dx. What is the change in length in a piece of length dx? This is the length of the piece. And if I integrate also, I get the same result. So there are two ways you can understand. And but this way, again, this is kind of recapitulation of your laws of motion understanding. And through these broken pieces also you can do. Now, yes, Vignesh, what is your doubt?
So in this case, we can directly use integration. Like when we use laws of motion, we don't need to.
Yeah, that's why I've done that. You understood what is integration here?
Yes, sir. Like I mean, we don't have to like calculate it separately for compression and.
No. So in this case, the way we are written here, just notice this is something when we write expression like this is valid for all values of x. In between, no other force is acting. Suppose in between apply another force also, then what will happen? We have some value from here to here and from here to that becomes a lot more complicated. But this is pretty simple. I've just written a force. So see, in very similar approach as we had in case of rod hanging under self weight. We can divide the rod into small pieces. Here also I'm dividing the rod into small pieces. Only thing what I've done, I have calculated force at a distance x from here. What is the force which will act at distance x from here? And once we have that one, very similar to previous case, through integration we can find out. Okay. This is more than actually, you won't find even this kind of questions also in majority of the books. Very rare you find this kind of questions. But mains also, you come across questions which are relatively different, relatively new. And this is a very simple application. That's why I have done this question. It's not very common kind of question you find in the books. Okay. Now we'll get into a couple of questions. Let's understand energy part also. We have done a similar question to calculate extension of the rod. So we understand when the rod is hanging under its self weight, tension will vary linearly from 0 to weight of the rod at the top. Here tension is 0. Here tension is becomes equal to weight of the rod. This we understand from laws of motion. So here again, this time what we need to calculate here, not the extension part. Extension is equal to W by 2 into L by AY. We need to calculate what is the energy stored. How would I calculate energy stored? I will calculate using energy density. So I'm going to use the concept of energy density. And because calculation of force as a function of y is easy, so I can easily find out force as a function of, so I can easily find stress also as a function of y. And I get energy density also as a function of y. And then I can integrate. So basically, I'm going to use energy density, which is equal to 1 by 2y into stress square. And since stress is varying, I will take a small element for which stress is constant. So again, a random piece, y to y plus dy. Again, we take a random piece and we'll calculate what is the energy stored in this piece alone. For tension here, we know what is the stress here. Tension to force is equal to, see, what will be the tension here? Tension is a function of y. We have done that earlier. I have written in terms of rho also. That will be equal to density into volume into g. And what is the volume from here to here? This part, volume will be equal to density into area of cross section into y into g. That becomes force. And if I divide the force by area, this is the stress which is acting in this region. So the part of a rod which is here will have a stress equal to rho into y into g, rho being the density. So what is the energy density here? 1 by 2y into stress square. That's the energy per unit volume. So what is energy stored in this element here? Energy density into volume of this piece. What is the volume of this piece? Cross-section area into length. So du will be equal to energy density into volume into dy. Into dy becomes the volume here. And then I integrate here, I get the total energy. This comes to total energy. What we have done finally after integration, weight I have written is rho ALG. Wait, sorry, this is capital G here. So this is something that you written, and you get the total energy, and very easily you can get this expression. And this is also a question which have come in the past. If, in case of metal wire also, if you pay attention to Young's formula, it has properties similar to a rubber band. But what is similarity with the rubber band? If you take a piece of rubber band, and as you apply force, its rubber band also will get elongated. And elongation is proportional to force we apply. And when you remove the force, it comes back to its own shape. And that's what even any material, any metal also, or any other solid material has similar kind of property. Only thing here, the extension is small. It's not easily noticeable, but it is there. So that's also there, and we have, that's why I said here, any piece of wire or anything which has uniform kind of cross section, we can treat like a spring. What is the spring constant here? Spring constant. So this question, let's go through this question. What is connected in this case here? At the end of a long metallic wire of length L. So this is metallic wire. It has a length L. It is tied to the ceiling. Other end we have connected a spring here, and spring has a spring constant K here. Okay, and mass M is suspended from here. And when it is unelongated, this has no tension, this has no tension. Suddenly I release this mass from here, you know what happens? Mass will start having such a motion. Mass hangs freely from free into the spring, area of cross section, Young's modulus, all are given. If mass is slightly pulled down and released, it will oscillate with time period T. What is the time period here? So what we need to do here, this is something, moment we see this is spring and this is wire, mind gets really confused. You need to think of this wire also as a spring. And what is the spring constant of a wire? The key point, so even wire is also like a spring. And what is K, the spring constant of the wire Kw, equal to Ya into M divided by L. That's a spring constant. Once I treat this as spring, now these are two springs connected in series, and series connection in of a spring behaves opposite to resistance. So what formula will apply here? We'll apply a parallel resistance kind of formula here. We'll find out equivalent spring constant. It is in series opposite to resistance. And once we find the spring constant here, the time period is very simple. So time period, what is time period equal to? Time period is 2 pi mass of the system divided by K equivalent. And what is the K equivalent here? K equivalent will be equal to K1, K2 divided by K1 plus K2. It is a parallel formula. This is something it has to be treated with as a spring. So that's what we need to keep in mind. Even though the deformation, let's see, even metal piece of wire has properties similar to what we notice in case of elastic rubber band. Only thing is K values many thousands of times higher, or maybe millions of times higher compared to rubber band. It is not noticeable, but it is there. Okay. Next question is something like this: a thin ring of radius r is made of material of density rho Young's modulus y, and the ring is rotated about its center in its own plane with angular velocity omega. We have some ring here, and like a hula ring, and the ring is rotated in its own plane. So this ring is there, and we rotate with some angular velocity omega. What will be the change in radius? What it says here, so this is something earlier, the radius is r here. And when we rotate this ring here, its radius will undergo slight change. The question comes, why would this radius change here? To understand change in radius, this radius basically, you need to first understand as I rotate the ring, the tension will develop in the ring. How would I calculate the tension? We have done already in case of circular motion. So tension is equal to, what is the tension? Is equal to force per unit length into radius, and force per unit length will be equal to, what is force per unit length? It's mr omega square, which m we have to take m per unit length. So this force per unit length will equal to lambda r omega square into r. That's the tension which will develop. And if the tension develops here, because the tension, circumference will change, and because of change in circumference, radius also will change here. So that's what the concept here is, and the value of what is small change in radius here. So radius also, see basically what is the perimeter? The perimeter will change. So change in perimeter will be equal to original perimeter. We'll use FL by AY. What is the F I'll take here? Tension will develop T in P by L by AY. Length will be equal to perimeter. Once I calculate whatever, if I take fractional change in perimeter, will be equal to fractional change in radius. Why is that so? Perimeter is equal to 2 pi r. For small changes, delta P by P is equal to delta R by R. So this is something to understand here. The entire part of the ring will be under tension here. And the tension we calculated in this fashion. And once I calculate tension, the key point here is tension is equal to force per unit length into R. And yeah, and tension is equal to, so basically fractional change, then we can calculate what is delta R equal to. Delta R equal to T into R divided by AY. Similar expression on perimeter. So that's the expression. Once you have delimited this expression, we can easily calculate here. And if you understand another way also, what is this term? This is strain. Strain by Y is equal to stress. Stress into A is the force. So we can easily substitute and get an answer here. Force per unit length is mass per unit length into R into omega square. Just for repeat that point. Okay, and this expression, and we get an answer. Now coming to shear modulus. And whenever you come across shear modulus, the figure, mental figure you should get in your mind is that of a piece of rubber. And if you have a slightly big piece of rubber, eraser what you use here, just imagine that you fix it, you hold it with your hand also. And what you'll notice here, if I apply a force here, and you pay attention, you'll find this vertical plane will get deformed. It will get moved like this. And when I apply force here, I can sense as if rubber is pushing my hand back. I can sense a resisting force applied by the piece of rubber. So two things I notice here. There's a deformation. This is delta X deformation. Force is acting in this plane of the piece of rubber. What is the area over which the force is acting? And area is lying in the plane of the force. That will be equal to top surface, top area of the rubber piece here. And there's a deformation here. So deformation is X here. X by L is equal to angle theta here. And that's called shear strain. Shear strain is this deformation. So shear modulus of rigidity, B is stress by strain here, and all modulus are like this, stress by strain. Here F by A, only thing what has changed is which A we should take here. This A area lies in the plane of action of force. So you can imagine this force is trying to give relative motion between different layers. I can imagine this material to be composed of several small layers, and the one which is trying to move one layer against the other layer is called shear force. And shear force, and that's the I can so delta x by L is called shear strain. Delta x and L are a mutually perpendicular direction. Hence, I can write the shear strain in terms of theta. So shear modulus is equal to force by A divided by theta. This is the expression for shear modulus. For most material, shear modulus is about a third of Young's modulus. Okay. There's no rule kind of thing, but it is always lower than Young's modulus. That's a point we keep in mind. Let's see how do we apply what kind of numerical we can solve using shear modulus. So now the piece of rubber what we are talking about has some dimension. You have this dimension here, and the lower surface is fixed to the surface here, horizontal surface. This lower surface is blue. And these are the dimension. This dimension is 2 centimeter, height is 4 centimeter, and a horizontal force of 16 Newton is applied. This is force is applied. So when we talk about on the top face, then the shear strain developed is this much. So we need to find what the shear strain is. The moment in order the shear modulus is given, so I just have to use shear modulus is equal to, I'm going to use what? Shear modulus is equal to shear stress by shear strain. Okay, that's what I need to use, shear stress by shear strain. Let me understand each part again better. What is shear stress? Shear stress is force by area. Which force and which area? Force is this 16 Newton. But which area should I consider? I should consider the area of the material lying in the plane in which the force is acting. That's the area I need to consider here. And if I take this area, this dimension is 8 centimeter, this is 2 centimeter. Which area here? Area will be equal to 0.08 into 0.08. That's a shear stress. And what is shear strain here? How would shear strain take place here? The shear strain, when we apply this force, it will get deformed like this. Whole thing will shift, and greater the force applied, greater will be the shift. And you just imagine here, if you have to keep it deformed, you need to keep applying the force. Moment you remove the force, it will again wobble. It will come back here. So it will also we'll come to that part also later. What is shear strain? This deformation is x divided by this height is shear strain. So shear strain will be equal to x deformation divided by which dimension? Divided by dimension perpendicular to the plane. This is the shear strain. That's what we need to apply. Rest all is simple. Shear stress area by area in the plane of the force. And this is what we get shear stress. Once you get shear stress, we apply, we can from using this formula, we can easily find out shear strain here. Shear strain will come from shear strain will be shear stress by G. This stress we divide by value of G, I get the value of shear strain. What does 1 by 15 indicate? It will make an, in radian terms, it will make an angle. So whatever height is, 1/15th of that height, the deformation will take place. Okay, and this is another question. Steel ruptures when a shear of this force is applied. The question is here, just you have just a sheet of metal. And it could be any other material, it could be a piece of wood also. Let's take as a shear stress is given. Some of you would have noticed whether be using a punch. You know, it is something like a punching machine. We use punching machine for making holes to piece of paper. And you know, how does punching machine go? It makes a circular hole all through the cross section of piece of paper. Similar way, we need to find out, there's also you need a punching force. And some of you have noticed whatever punching machine also, if you have 10 sheets of paper, you need a different force. But if at a time you want to punch the whole 30 sheets of paper, you need to apply a greater force here. So there also, which is what is the strength which is coming into picture? Shear strength is coming into picture. So what it says, it has a maximum shear stress it can bear is this. So whenever shear stress of greater than this applied, basically shear failure will take place. Let's understand what does shearing mean. shearing mean? So what is the force needed to punch a 1 centimeter dia hole in a steel sheet of 0.3 centimeter thick? So first we need to imagine what is the area. This is shear stress. To find force, I need to multiply this stress by area. How is this force acting and which area do I need to take care? So to understand the area, first we need to apply understand what does punching mean. So punching basically means suppose I make a punch here, and you know that you can use a kind of cylindrical rod to punch a hole. So when I punch a hole of radius r, it makes something like this. It will look something like this. So which is the area through which punching has been done? What is the area here? So after you punch a sheet, you will see fresh mark here. Some part of the metal has been you have been shone through. And what is the area will be? It will be area of hole punched or area through which shear rupture has taken place. Is cylindrical in shape. And this, if you visualize, you can see fresh marks here. Metal will look, if metal, most metals do get like a piece of iron, it gets oxidized. So when we make a punch hole, this area will look fresh, and that's the area we need to take care. What would this area be? So when we talk about, so if you keep a rod here or something like punching machine, if you do not apply adequate pressure, it will not shear through the plate here. You need particular force here, and the force is really large. So if I apply that force only, it creates shear stress along the surface and it makes a hole here. So force is equal to maximum shear stress into area of shear. And what is the area shear? Area where surface will have fresh metal exposed. So area will be equal to perimeter into thickness. That's wherever we come across this question. And shear modulus, very rare questions have come, but it does not mean we can, but variations are limited. So this is something not, if you understand this question, um, I don't think it looks too difficult. So when we talk about how does it happen or don't overthink it, but at least have a basic understanding of what a shear means. And the word shear itself comes from things. So when you use a scissor also, what does scissor do? Shear, if you have metal plate, if you use a scissor also, it is shears through. It shears through plate. Why does it shear through? Basically, what kind of stress it creates? It creates a shear stress. So something similar. So scissor makes if you take metal plate, if I use kind of scissor kind of material to make a hole, cut through, if I cut a sheet of the, in that case, suppose I cut this sheet into two pieces. This would be the shear area. The force which need to be applied by a shearing machine, and shearing machine could be like a vertical plate also. A sharp vertical blade kind of plate also. We bring it in the top of this metal plate and apply a large force, it will shear through. Like guillotine also the word which is used here. And what will the shear area? Width of the plate into height. And shear strength multiplied by the area is the force needed to shear off one piece of metal plate. That's a force. And this also past JEE advanced question, a little tricky question. Let's see understand what it means. So you have kind of a piece of rubber here. Rubber, we have discussed about rubber piece, eraser. This may be a large piece of rubber, and we understand here, if we apply a force here, the angle theta is proportional to force, which means at angle theta, it will apply a resisting force. And resisting force is proportional to, that's a force rubber piece applies. When you deform, it tends to come back. And if you apply a force, deformation of delta naught theta naught, and if no loss is taking place, what will happen? It will keep vibrating kind of top surface, and whole piece of rubber will jiggle kind of thing. So this it will vibrate like this. So here, let's understand what the question is, and you may have some question variation from this. Key point here is it will apply a resisting force proportional to shear strain. And shear strain is nothing but angular deformation. Shear strain and angular deformation are same. Highly rigid cuticle block of small m inside LX is fixed on the other cuticle block B. So this is block B, and this, and on top of it another mass A is placed. Okay, and block B of the same manner, it has low modulus of rigidity. When it has low modulus of rigidity, then only it will have more shear deformation. Otherwise, deformation becomes negligible. And lower face of is completely covers the upper face of B. These two are identical. They are placed on the top of B, so common surface is a common area. It is placed like this. Lower place is rigidly held. The question wordings are little complicated. Figure is not given. So if something like wordings are given, you need to visualize what this indicates. A small force is applied perpendicular. So what we do here in this case, we apply a force here, which deforms a lower piece of the rubber. Upper piece remains always vertical, mounted on lower piece. And after we give it angular deformation and suddenly leave it. It tries to come back and it exerts a force. Earlier, this force was registered by F. Now this force is even moving this block A as well. When we apply this, because earlier, even as it moves back to mean position and overshoot and start vibrating, the block A, which is placed on the top of block B, will also oscillate. And since this deformation X is proportional to force here, it will undergo SHM motion. The whole thing is what is the time period of SHM motion? And force on the block B is equal to shear force exerted by A when the shear strain is theta. So whenever how do we calculate such a motion? Such a motion, we always use force Fx is equal to minus m omega square x. I'm going to use that one only. Fx defined by B. And what is Fx here? On which block? We are calculating Fx on block A minus m into omega square x. So what is the force which is acting? Force acting will be shear modulus into shear strain into area. Let's write here shear modulus is eta and force is negative opposite to direction x. Shear strain is x by L here. This is the height of the lower block, lower B block. And area, common area is a cube, this area is L square. Which is L square area? Area lying in the plane of the plane in which force is acting. So when equate to minus m omega square x, I get the value of omega. So this is one typical case of such a motion created by what you call a shear property. And I guess this question had come in JEE Advanced maybe about 15 years back, 10 years back. And since then, nothing else similar. But yes, but once anything which has come in the past, you may come across a similar variation. The dimension may change, the height may gain 12 or something. But once you understand how do we calculate this force, what force this block of rubber exerts when it is given a deformation, that becomes a resting force, and that's the force what we use for calculation of SHM. And this kind of question also can be solved. Okay. What is bulk modulus? Bulk modulus is, this is something what we have done here. This was Young's modulus. In case of bulk modulus is when the force is applied on all surfaces and pressure is equal. How do we apply such kind of force when object is subjected to liquid pressure? So suppose you take a metal bottle, metal sphere, and you take it to certain depth in the water. In that case, force will act from all directions perpendicular to surface, and it will produce some kind of volumetric change. So we are talking about that. And bulk modulus we had dealt with earlier also. It is equal to minus delta P by volumetric strain. Bulk modulus is pressure divided by volumetric strain. And unlike previous cases, see all cases so far what was happening, when we apply a force, the dimension when with positive force and elongation, both are in the same direction. Here what we notice here, when we apply a force here, the volumetric change, for positive pressure, volume change is negative, as we use a negative sign. If you want a bulk modulus is a positive quantity. Negative sign indicates the increase in pressure leads to decrease in volume. And inverse of bulk modulus is called compressibility. If bulk modulus is high, it means if this value is high, it means volumetric deformation is small. So inverse of that is compressibility. So gases have large compressibility, millions of times more than solid. So this is something, change in volume is easily noticeable in case of gas, not so much in case of liquid and solid. A simple application, solid sphere of R. This also is similar to questions which have come in the past. Solid sphere of R is made of soft material of bulk modulus K surrounded by a liquid in a cylindrical container. A massless piston of A floats on the surface of the liquid, covering entire section of cylindrical container. When mass M is placed on the surface of the piston, it compresses the liquid. What is the fractional decrement in radius of the sphere? And many times the question comes, sir, they do not give a figure. So first, we need to understand what is this whole story. This whole story is something like this. Let's visualize what this whole story is. So basically, there is a solid cylinder of solid sphere of radius r. Okay, we have a solid sphere of radius r. We have solid sphere of radius r here. Okay, fine. It's made of bulk modulus. Bulk modulus is K here. It's surrounded by liquid in a cylindrical container. Make a cylindrical container. So we make a container here. So we made a container also nice. So whatever is given, either we draw or visualize. We made a cylindrical container here. And cylindrical container. Okay, what else is given? Nothing. A massless piston of area floats on the surface of the liquid. So there's a piston here. And initially the piston, this is a piston which is floating here. And this is what is given entire section of cylinder, and this area is given as A. When mass M is placed on the surface of piston, if we place a mass M here, what is the effect of placement of mass M here? And this we have done from fluid. When we place a mass M here, liquid in the bottom of pressure on the bottom of the piston will increase, and everywhere in the liquid also pressure will increase from the Pascal law. So there's an increase in pressure. What is delta P here? Delta P is equal to weight divided by area of cross section. So entire story is only to tell that increase in pressure is equal to mg by A. So if I have increase in A, we can calculate what is the change in volume, fractional change in volume. What is this pressure here? Mg by A. Fractional change in volume, delta V by B. From this equation, it is equal to change in pressure by B. So this is mg by AK. That becomes fractional change in volume. But volume is related to radius and 4 by 3 pi r cube. And whenever quantities are related, small changes are also related. Fractional change in volume will be equal to 3 times delta by r. Since I need here fractional decrement in radius of the sphere, I write in place of delta V equal to delta r by r. So I get the value of delta r, this whole number divided by 3, and negative sign indicates a decrement. I get the value of expression easily. So that's the application of bulk modulus is.
So what exactly does delta P mean, sir? Is it like the pressure before applying
No,
and
change in pressure. When the pressure changes, volume changes. So this is change in pressure, this is corresponding change in volume.
so like if it's at a depth h, then like
Yeah,
rho g
see,
h is not
we are
included
asking,
anywhere.
see, it had some radius r. When it is at depth h, it already had some radius there. We are not concerned with this. When we plate the mass m here, it becomes rh dash. What are we concerned? We are not relating these two. Which two quantities are we relating here?
Okay, the second and third one.
Second and third. So
Okay.
basically, when we say delta H, when we calculate delta V volume also, which delta we are calculating? Delta V is the volume when it is placed at depth H. That is my initial volume. And what is my V dash here? V dash is after I place this mass M here, then what is the volume? So when is delta P? Delta P is corresponding to, you need to define which two states we are related to. The two states are when the sphere is at depth H and at the same depth when mass M is added, that's a change in pressure, delta P. So delta and P and delta V are related to each other. So corresponding to initial pressure, initial volume, corresponding to final pressure, final volume. And change in pressure is delta P and change in volume is delta V. Okay. And one more question here, and we always talk about basically we say no, liquid is incompressible, hence its density will not change. But now we are talking about yes, everything is compressible. If everything is compressible, everything has some finite bulk modulus. So yes, volume will change and hence the density will change. So this question is estimate the change in density of water in ocean at a depth of 400 meters. So let's understand. If we know the property of water. For experiment, easily it can be found out, and we know this value is defined. The modulus of water is this. So what is the change in density of water at a depth of 400 meters? Given the density of water at the surface is 1000 kg per meter. So what we have to visualize here, this is something simple. Let's see what does it mean here. So this is my sea level. And if I imagine some small volume of water, okay, it is compared to, see, if I take some volume of water here, this volume of water will have a pressure equal to atmospheric pressure. But this is at a depth of 400 meters. So this will not have the same pressure. This pressure will be equal to atmospheric pressure plus rho gh. And this had volume V, this will not have volume V, this will have a volume V minus delta. So as the pressure, so earlier I have imagined some liquid volume, it had V volume. When it was atmospheric pressure, it had volume V. In the same liquid I have taken to depth of 400 meter. So this pressure becomes so much. What is change in pressure here? I am comparing this with the sea level. Change in pressure is equal to rho gh. And when you have change in pressure, it will lead to change in volume. And since the density is equal to mass by volume, change in pressure, if the volume changes, pressure also will change. Right? If my volume changes, the density also will change. And how are these two related? So basically from change in pressure, I can calculate change in volume. And how is change in volume related to density? If these are the relationship, whenever quantities are related, delta rho by rho, fractional change in density will be equal to minus dV by d. That's the relationship I will use. That's all. What is delta P? We should understand what is delta P here. And delta P will produce delta V here. So modulus is equal to minus delta P by delta V by V. And the change in pressure is equal to, we should understand which two, we have to compare which two are we comparing. We are comparing sea level with 400 meter depth. So this is change in pressure, 1000 into G into D. So this is the change in pressure, 4 into 10 to power 6. What is fractional change in volume? Delta V by V. I can find fractional change in volume delta V by V. So whatever volume the liquid had at the surface, when the same volume is taken down below, its value will shrink. Delta V by V I get from here minus delta P by B. So this is negative. This is okay. So very simple. Just we written the value. This is delta P by. Oh, sorry. This is 10 to power 9. Okay, 10 to power 9 here. Okay. So this is fractional change in volume. And then how do we get density here? That's what I written here. Density rho is equal to m by v. So delta rho by rho is equal to minus delta v by v. One I have from delta v by v. This is delta v by v from here. And negative of that. What do we understand here? As the volume shrinks, density has to increase, which makes sense. So delta rho by rho, if I find, since I know the value of rho, I can find delta rho. So change in density becomes increases by 2 kg per meter cube at a depth of 400 meters. From not 1000, it becomes 1000. So you notice here, that's what the compressibility is. And even with such significant change in pressure, change in density is so small, and that's why we take it virtually incompressible. Okay. So I'll take a break here. Okay, sorry. Let's see. I think one more question. Okay. I think it takes a little while. It takes 5 minutes to 10 minutes more. So I'll stop here, and we'll continue from here.